Hey, you're muted right now.
I got it. Should be better now.
All right, yep, I can hear you.
All right, great. Uh, your screen is paused, right? Resume. Okay, okay, good. All right, I am recording now and my volume is on, so all is good. Let's take a look at the exam. Um, look at the YAML version. All right. So the idea is to look at the various executions, and I tried to take all the read write stuff and move it into the queue just to give you something a little different, so that you had to, couldn't memorize and had to engage your brain. So the idea is first is it linearizable? So I want to so the problem is I can get these two in order, right? I can say NQ1 and DQ1, and that's fine. But then I have to DQ2 before I NQ2. So it's not linearizable, right? Quiescently consistent. Well, the only things that are overlapping are these two. So those and juggling those doesn't help me in any way. So it's not quiescently consistent. Sequentially consistent, I can just take this event, this DQ2, and I can slide it to the right and make it work. So it is sequentially consistent. In this next one, is it linearizable? Well, I guess I have to put first NQ2 and then DQQ2. So there's no way that's going to happen. And that with linearizability. Also with quiescent, well, with sequentially consistent, I can't slide this Q.NQ2 to be before here. But because these things are all overlapping, I can shuffle them and make it quiescently consistent. And then this next one is just straight up linearizable, right? So I can just say NQ2, DQ2, NQ1, DQ1. Easy. And then this last one, I struggled to get this one. I tried to figure what I wanted was one that was quiescently and sequentially consistent, but not linearizable. And it just took me like half an hour to figure it out for whatever reason. That something that would give me that answer. But so what I can do, right? If it's quiescent, I can just juggle this. So I NQ2, DQ2, and then NQ1. I'm sorry. Um,
You have to swap DQ2 and DQ1 for a thing.
hold on just a minute. How can that possibly work? I could have sworn I had this. Wait a minute. So, okay, let's go back. Let's back off for sequentially consistent. Sequentially consistent, I can just slide this all the way down, right? And that should work. Um, but it looks like I failed here because I can't get these two in the correct order. All right. Well, I think my key is wrong. I thought I made it quiescently consistent, but I guess I failed.
Somehow not quiescently consistent. I feel like at some point in the test it was a way in the base.
I could have sworn I believed I had it too, but now as I'm staring at it, I can't make it work. I think in my head, I when I was doing the quiescently one, I swapped these two, in which case it would even be linearizable, I guess. But okay, so this one should be just quiescently consistent, just sequentially consistent. It's the only way it works. Oh well. Um, all right, so I think this one is unchanged from the quiz, so I shouldn't need to say anything there. I think the next one is similar to the quiz, but I think I changed something. So in OpenMP, by default, dynamically allocated variables, malloc free, new delete, are shared. Pragma-critical is for mutual exclusion. A reduction combines data from multiple threads, correct. It is impossible to create deadlock with MPI send and receive, false. It is necessary to use MPI wait with MPI I receive, true. It is necessary to use MPI wait with MPI receive, false. A ghost zone is a place to put dead freed data, false. Ghost zones are exchanged to synchronize data, true. Any questions? All right, so RMW mul add. Consider this RMW instruction with the semantics of the code below. What is its consensus number? 3 or more. Because you can easily arrange to say do ×2 + 1 ×3 + 2, whatever you want. And by doing something like that, you can create something that does not commute and which can distinguish 3 states easily. Any questions? Not yet. All right. Well, you are. What speedup will be achieved for a code that is 80% parallel when run on 4 processors? 2.5. You shouldn't need a calculator for that. So you've got the 20% that's serial. You've got the 80% that's parallel. On 4 processes, that 80% becomes 20%. So 2/5, 2.5. Or 5 halves rather, 2.5. Make sense? All right, good. Mark all the options that are true about this lock. It works perfectly for 2 threads. What I did is I just swapped the victim and the check for victim. If you swap both of those things, it's okay. So that one works. It fails for 3 threads, of course, because it's a Peterson lock. The CLH lock, I mean, you can just get that. Oh, I'm sorry.
And then 8 is all the way at the top of the stage.
I see. Sorry. So I kind of figured that of the algorithms we studied, this is one of the shorter ones, and you should be able to take the lines and put them in the correct order. I think only one person succeeded in that completely. But the first thing you're going to do is you're going to get your Q node, right? You're going to set it to locked, and then you're going to do your get and set to put it into the queue. And then once you've done that, you've got your predecessor, so you can set your predecessor, and then you can do your while loop, right? And then in the unlock method, you're going to get your Q node, and you're going to set it to the locked to false, and then you're going to set your predecessor, your my node from your predecessor node. Right?
Yeah, I had to go and look back over that.
Yeah, but that's just, you should be able to just look at that. Oh, and I've got the answers right below there. Of course. And I had some partial credits that I put in here for a couple of different orders.
These. Bottom.
Yeah, okay. So you want to skip over the true false? Is that what you're telling me?
Those are my questions.
All right, let's look at the foos. Let's look at the foos. All right, so the foos were designed to sort of hit all the different things. So foo 1 is going to be this is a non-working version of the Peterson lock, right? It's going to deadlock, right? Because they'll both raise the flags and then look and wait for the other one to have its flag down, and they'll just sit there forever, right? This is the first thing we discussed in chapter 1.
Yeah. Why I got some of these wrong is because I read it and my brain skipped over the word parallel and thought they were running one after the other.
Ah, well, that's you need to have the process the recall on your brain. Okay, so what's the definition of weight free?
Weight free is like starvation free, but for lock free.
Right, but what is the normal phrase that we use to describe weight free?
Every method turns in some finite number of steps.
Yep, completes in a finite number of steps. This has 10,000 steps exactly. And then it's done. So it's weight free. It's weight free. Because it's guaranteed to be done with that when that 10,000 steps finishes. Lock free potentially takes forever.
They both are a finite number of steps though?
Nope.
Wait,
You have to wait for another thread to unlock.
Only weight free completes in a finite number of steps. Let's see, foo 3. What am I doing here? Oh, this one is lock free, right? This one is trying to increment the count variable in a thread safe way. But that while loop could execute infinitely if the other thread keeps coming in at the wrong time, right? You see that?
So why would it be lock free and not deadlock free?
So the reason it's not deadlock free is if the other thread goes away, this is guaranteed to complete in a finite number of steps, right? This is the concept of deadlock free and starvation free is those are describing blocking protocols, and this does not block, right? And the way you, as I say, the way you identify blocking is you think about this. If the other thread disappeared at some inconvenient time, could my calculation still proceed? And with this, the answer is yes, right? The only way this fails is if between the time when I get the value of count and I attempt to update it, somebody else comes in and updates it. If nobody else comes in and updates it, then I succeed. Foo 4. What is going on here? I think, what did I put? I put starvation free. There's a typo in the exam here, I guess. This was meant to be a Peterson lock. Shoot. I forgot the victim equal me part. Well, that's supposed to be there. Darn it. How is it that I can stare at my exam while I'm making it and not see these things? All right. That's what I meant to type there. Without that, I guess it's, what is it? Flags. With the victim equal me, it should be starvation free. That's what I was expecting it. But without that, it's kind of not.
3 points.
I'll have to think about it. All right. And then the last one is deadlock free. This is also a protocol from chapter 1. This was, when one thread decides to be a gentleman.
Is it also starvation free?
No, because the one who's deferring can get starved. Does it all make sense now?
But I think my brain just mixed up starvation, lock weight, and deadlock free, and it just got jumbled.
Yeah, so anyway, I figured this was going to be a tough question. But I figured it's an important one because you need to, if things are just in your head in an abstract way, you might never really understand them. And this is a way to make them concrete. At least that's the way my brain works. I need an example to understand things. At least one. All right. Anybody else have anything to ask me about relevant to the exam? Which of the locks are fair? Bakery, CLH, MCS 2 counter, A lock. False. Are we good? All right. Do we want to talk about the homework? All right. This one, yeah, it was again turned out to be, I think I've signed this problem before, but I never really realized that I was doing it wrong before. And so this year I made it explicit so that that wouldn't happen, so that we'd all get it right. Really? I was going out of my way to be very explicit and clear.
Like, make one for ourselves.
Well, I gave you that so that you could use it.
Yeah. I realized that it didn't work if I didn't use the words, like at all.
Yeah, so but my tester is important, right?
Yeah, I was thinking, just need to test the method out of it, but
You need the whole thing. So here's my consensus for object. And so I have my bin consensus, right? Which is this whole long thing here, which is my binary consensus. And I designed this so that it could die at inconvenient times, which is the key thing that you need to make this difficult. And so what I do is first I get my ID and then I set my proposed value. And then I get this other thing that I call my proposing. That's what I'm currently proposing. And currently I'm proposing myself. That's the way I start. And then I get the lowest bit of my proposing thing. And I try to call, so I have my list of consensus objects, which I think only needs to be log the number of the number of threads I want to solve for. But anyway, so I'm going to propose that binary value that I got by looking at the lowest bit on consensus object 0, right? And then I'm going to see if I won or not. And if I didn't win, then what I have to do is I have to find a new value to champion, right? Because I know that mine has lost, right? The one I proposed has lost, so it's kind of like I was running for president. I've been eliminated from the race, but now I get to vote for one of the remaining candidates. So I'm gonna figure out which one I'm gonna vote for. And so I made this little loop to look through, and I wanted to get I need to get one that is not null. In other words, the thread has moved, and that the proposing underscore and 1, the bit on it, is equal to the result that I got, right? So I want to find one that's still valid after this first consensus attempt. And that's the criteria. And once I find that, then I break. Okay. Next, what I did is I find to solve the second part of this, right? I need a second consensus object. And the bit I'm going to propose, I'm going to first right shift the bits, and then take the lowest one again. And that will give me the one that I want to propose on the second consensus object. And then the winner is going to be at 2 times R2 plus R, right? So of those two things. And so then I can say propose.getWinner, and that will be the winning value. And then I have an assert statement there. just to see that I know what I'm doing what I think I'm doing, and I return the winning value. Does that make sense? So the key difficult step, I think, at least for me, is getting this right.
Mine,
Okay.
so I took inspiration from the use tree.
Mm-hmm.
And I did, like, basically the same thing except for like fighting for a lock or fighting for attention, so two threads would decide who's a winner. Those would go into the next round, who's the winner, who can, and if you fail to get any of the consensus, if you're last, then you would have to wait for the winner to be decided, and then the winner would say their thread ID, and everybody gets that.
I can't follow that logic from just your verbal description. But the point is, though, I think that the tricky part about it, this is kind of using well, it's always using a selection of binary objects, but the trick is to not propose an invalid one, right? So what the testing artist is trying to make sure you don't succeed in doing is having a thread win that never moved, which is easy to happen, which will happen easily if you don't have this logic here.
If the thread never moves, then
It can still be if you just do straight up bind. If you just do the bits and then try to solve for the winner that way, you can easily stumble across the case where somebody that never moved wins. You have this step where I pick my new value to propose is key. And then the trick was, after getting this right, to generalize it. And so there's a log2n method here that you can, if you're tricky, it's 31 minus integer dot number of leading zeros. That'll give you the log to the base 2. And this is bit at, so that's going to shift you n bits and then ampersand with 1. And what I'm going to do this time, I'm going to do the same basic logic. My proposed, I don't need to use get and set here. There was a time when I was flailing around trying to make things work, and I think I could just change that to a set. Anyway, so what I'm going to do when I go through this step is I'm going to have my proposed bit value. So I'm going to say what I'm proposing, right shifted the number of steps, and then 1. So I'll get the next bit each time. And then I'm going to get the decided bit value, which will be the consensus object for this step with the proposed bit value proposed. And then I'm going to create a mask by turning on, by ORing on the decided bit with the left shift of the step number, and the low mask is going to be just a 1 with the left shift number. So the idea is, after 3 steps, the low mask will be 1, 1, 1, and the mask will be some combinations of 1s and 0s on those last 3 bits. And then I'm going to see if my proposed and decided bit value are different. And if they are, then I'm going to go through all the different threads, and I'm going to look for one that isn't null, and for one whose low mask, so this thing that's all 1s, this low mask and the value proposing is equal to the mask. So that means that it matches all the bits that have been proposed so far. And if I find that one, then I set that as my new proposing value, and I break. And then at the end of this, I can find my winner by just looking up the mask, right, in the array. Does that make sense? All right, I didn't actually work the second part of this. I forgot to do it. So I'm just gonna go ahead with the slides for today, and we can discuss that next time. All right? Any other questions on this? Does it make sense? Are you familiar with these various bit operations?
That's straight.
So I advise you as computer science students to make yourself familiar with them. Maybe I should talk briefly about them at some point, but left shift is going to just shift the bits to the left, right? That's that double arrow to the left. And if I put one left shift, shift n, that's the same as 2 to the nth power, right? Because the bits are powers of 2 in memory, right? And then we have or equal, which is the same as low mask equal low mask or this value, right? It's just kind of like plus equal, but for the logical or. And you can do the same thing with and equal. And if you want to turn a bit on, you say or equal and the bit. And if you want to turn a bit off, you say and equal tilde the value of the bit, because tilde does a negation of all the bits. Is that okay with you, Reagan? Okay, so all right. So if I say, if I say, well, all right, maybe I'll try to talk find a little pointer to something about basic binary logic, but it's something that you really need to have as a computer scientist. And I don't know that there's a course where they explicitly teach it to you.
They do. Been like 2 years for me since I've been.
Which course did they teach it in?
Organization design.
Okay.
It's also very different depending on which professor you get, because they're always swapping in and out, and sometimes it's like the professor is really good, and sometimes the professor is like really bad.
Well,
It's operation.
yeah, so you need to know logical or, logical and, exclusive or. You need to know tilde versus minus. And left shift and right shift. And those are the basic things. And just how to use them and how to combine them is the trick. Yeah. Yeah, it's just and or and exclusive or. And tilde is kind of like not on all the bits.
What's the difference between doing a tone 1 bit versus the bang exclamation? Is that similar?
Bang is usually just means not. So that's going to that's going to be so you can convert an integer to a truth value, and 0 is going to be false and anything else is going to be true. But like if you do 0, bang 0, it should be 1, right? So it's only going to do that one sort of thing. But a tilde will flip all the bits. Anyway, some basic bit manipulation is something that you should all know how to do. And like this sort of thing should not look mysterious, which I was hoping it wouldn't. But if it does, we can work through that. All right. Let's go to
Never seen it. When we did it with 3501, we were just given like a binary value.
I hate that. I understand that the information was presented, but for me, without a code example, you might as well have not said anything. Yeah.
The entire class is like binary math.
Yeah, and binary math is very useful for, keeping track of bits for various pieces of logic and code is a very useful thing to do. And yeah, as I say, for me, everything I do, I need to have an example, and I need to have a working example. The thing I hate is somebody says, "Oh, here's how you do it," and they give you a snippet of code that you like the slides, where you have to supply a whole bunch of other stuff that just isn't there, and you don't know what it is, right? So I always have, with the codes in this class, I always have a complete code for you to reference. All right, let's take a look at lists. All right, so we've talked about spin locks and critical sections and so on. And the basic dream is that adding threads shouldn't lower throughput, right? You should make your code go faster. But you have to make sure you understand contention effects and what's going on. And if you make everything, if you wind up making things work by making it all sequential, it's going to wind up going slow. And that's sort of our first approach to anything, though. So we're in this class, we're going to look at a set implementation. And the first thing to think about is the coarse-grained implementation. You just have one lock. You can't access the set without the lock, and whatever you do is guaranteed to be safe. And if you're building an application for something, you should always do the simple, safe thing first, right? Always, always, always do the simplest thing first. And then later, when you want to do a complex optimization, you do it in a way that factors that you can just drop in a replacement of that one part, right? But you need to have the simple thing that works. So that just so it's not, even though it's bad for parallelization, it's still useful. Why is this not advancing? What is going on? Oh, here we go. Okay, so with coarse-grained synchronization, things bottleneck, they stand in line. And adding more threads does not improve your throughput, and it's just going to probably get worse. So why even use a multiprocessor? I mean, some calculations are inherently parallel and some are not. In this lecture, we're talk about 4 patterns, which are a bag of tricks, and they're kind of useful in a number of different situations, but this is like the simplest version of them. And you'll just have to recognize these patterns on your own in your real life. And these are for highly concurrent objects. And the thing you want to have is more threads equal more throughput. So our first way to improve on coarse-grained synchronization is with so-called fine-grained synchronization. And instead of using a single lock, we split an object into independently synchronized components, and methods conflict when they access the same component at the same time. The second technique we're going to look at is optimistic synchronization. I've had the worst sinus problems the last couple of days. Second is optimistic synchronization, which is going to search without locking. And then if you find it, you lock it and check that things are still okay. And if they are, then you're done. And if you're not, then you start over. And it's usually cheaper than locking, but mistakes can be expensive. And the third is lazy synchronization. And so what we do is we're going to postpone the hard work, and removing components winds up being tricky, but we'll talk about how to do it. We're going to do it through steps: logical removal and physical removal. And there are several reasons why I think the third way is the best way, but we'll get to that. At least in this case. So, okay, and then the fourth is the lock-free synchronization. So we don't use locks at all. We use compare and set and relatives. And the advantages is, we don't have to rely on scheduler assumptions and so on. We don't have to worry about threads going away. But the disadvantage is it can be complex and the overhead can be high. All right. So the way we're going to illustrate these patterns is we're going to use a linked list as an implementation for a set. And the set is going to have 3 methods on its interface: add, remove, and contains. And add will put something into the set, remove will take it out, and contains will see if it is in the set. And in Java, that looks like this. And they all have a Boolean return value. So that's the add, the remove, and the contains. Next, we have a list node, and it's going to have an item, an integer key, and a public node next. And we're going to have what are called sentinel nodes. sort of minus infinity to plus infinity values that mark the beginning and the end of the list. They're not actually part of the set. They're just sort of markers, and they're always going to be there. And we're just going to use them to keep our logic straight when we're traversing. So this would be a set that contains A, B, and C that we're looking at now. And so when we reason about concurrent objects, we want to have things that are called invariants. And that's a property that's always true. And that's a very useful concept to have when thinking about any kind of programming construct. So the idea is it's true when the object is created, and the truth is preserved by each method and each step of each method. And specifically, invariants preserved by our list are going to be, well, the invariants are going to need to be preserved by all three methods in our set. And most steps can be trivial. Usually there's one step that's tricky, and it's often a linearization point. So the invariants only make sense if the methods considered are the only modifiers. So we want to make sure that, we know exactly how the information is being modified. Otherwise, the invariant might not hold. And languages can help us with this, right? By giving us protected and private and so on. So we got to make sure that when two threads are doing operations at the same time, they don't interfere with each other. An add doesn't, a concurrent add and a remove both have to succeed, right? One of them can't prevent the other from working. In this particular lecture and the things we're discussing, garbage collection helps, right? This gets just at least twice as complicated if you also have to think about garbage collection. If you also have to think about memory management yourself. So Java helps out here. So let's see. We have our abstract data type. So we have a concrete representation and an abstract one. So the set AB, right, which mathematically you could write like this, in our code looks like this. We have Sentinel, points to A, points to B, points to Sentinel. And yeah, so that's just the same thing shown in two different ways. And we talked about what Sentinels are. So the invariance that we want is that the Sentinel nodes are always there. The tail is reachable from the head. The nodes are sorted, and there are no duplicates, right? This last thing is necessary for it to be a set. So we have three invariants here: tail reachable from the head, sorted, and no duplicates. And so we say we have this abstraction map. We can say that our set contains X such there exists an A such that A is reachable from the head, and A.item equals X. So we can sort of talk about it that way as well. Okay, so here's two lists. We can add and we can remove. So in this top one, we're adding A, and the way we add A is we create this node B, we set its next pointer to C, and then we swing the next pointer from A to point to B. And we can remove B by taking the pointer in A and swinging it around B to point to C. And the garbage collector will see that the memory for B is cleaned up. All right, so for coarse-grained locking, we get one lock, and then we do everything. And then and it's simple, but all the other processors stand behind in line sequentially, which, it's easy it's the same as having synchronized methods. One lock to rule them all, if you want a Lord of the Rings reference. It's simple, it's clearly correct, and that much deserves respect. And as I say, you always need to have something like that as a fallback when you're coding, to find some kind of ground truth, right? You have a bunch of components in your system. Which one is misbehaving? Is it my complicated wait-free lock? Yes, probably. It works poorly with contention. Q locks or some of the other special locks we saw could help, but bottlenecks can still be an issue. Fine-grained locking requires careful thought, and we have another Lord of the Rings reference here. Do not meddle in the affairs of wizards, for they are subtle and quick to anger, right? So we can easily run into trouble with fine-grained locking because of the subtleties of locking. But the idea is that we split the object into pieces, and each piece has its own lock, and methods that work on disjoint pieces need not exclude each other. All right, so the thing that we're going to do with fine-grained locking is what we call hand-over-hand locking. So first you lock the sentinel node, then you lock A, then you lock B, then you lock C. And you're going to hold two locks at once. And so when you remove a node, right, what you're going to do is you're going to get the lock on A and B, where I'm removing B, and then I'm going to swing the next pointer on A to point to C, right? I'm going to point it to B dot next. So why hold two locks? So let's look at concurrent removes. If we don't use two locks, right? So we go one at a time, we're going to remove C, and this one wants to remove B, right? So what do? So B has the lock there, and B is removing C, so it swings B's next pointer over here, which is a perfectly reasonable thing to do because it's holding on to the state that it's modifying, a lock for the state that it's modifying, right? But what happens is A swings its pointer past B to C because it's trying to remove B. And it can do that because it's only modifying its own state. So what happens is the removal of C gets lost when these two things happen concurrently, right? That's why we lock two things. And this is a very interesting example. It's taken me a while. I've been pondering on this for the years while I've been teaching this course. And one of the things that's going on here that you don't realize is that there is an implicit state in B, and that's the meaning of that state is reachability, right? I'm still reachable from the head. And even though that state isn't explicitly represented, logically it's there, and logically you're changing it. And if you don't have the lock for it and it changes, you're in trouble. So I think that's kind of an interesting realization, at least for me, that there's this implicit state hanging on B.
Can you say that one more time? Sorry.
Yeah. So there's this property of B, right? Whether it's reachable from the head or not. And that's kind of like a state, even though it has no variable that represents it. We have no, reachable bit that we mark or unmark. But nevertheless, the program knows it's there, right? It's sort of implicitly there. And if we don't lock it, then we run into this problem, right? Because what we're doing when we change this next pointer is we're implicitly changing this property of the next object, whether it's reachable or not, if you want to think about it that way.
Okay.
Okay. So the problem is to delete node C, we swing B's next field, and someone deleting B could concurrently point to C. And so the insight is that if a node is locked, no one can delete the node's successor. And if a thread locks the node to be deleted and its predecessor, then it works, right? So we go through this with two locks, and now when I do my delete of B, it works because, the way I like to think about it is B has an implicit state of being reachable, and I'm changing that on B, as it were. And so I need B locked. I don't know if that quite makes sense to you, but that's the way I've come to think about it. Anyway, so if I lock these two things, then I don't get into that problem I had before where I had a lost delete. Are you all with me? Asher, are you with me? I wonder if he is. Oh, well. Okay, so now we're removing a node, right? And we must acquire the lock for B to remove it, and we can't acquire it because C is doing its thing. And now C has done its thing, and now we can remove B, and then it all works correctly. So with two locks together, it works correctly. And the code for that looks like this. So we have for every key we're So one of the things they do in this slide is they get a hash code for each item in the set. And what they're going to implicitly assume in most of the slides is that the hash code uniquely identifies the objects. So just keep that in mind. Hash codes don't normally uniquely identify the objects, but in this example, they will. Okay, and we're going to have a predecessor and a current node, and we're going to have our try finally to do unlocks, as we should. And then we're going to have a bunch of stuff where the ... is, and that bunch of stuff looks like this. I have the pred equal this dot head, and then pred dot lock, and cur equals pred dot next, and we do cur dot lock. And then we traverse. And the traversing looks like this. So we say, well, the current key is less than or equal to the key, that we're going to keep looping. And then if we find the item is equal to the current item, or the current key is equal to the key, then we're going to say that the predecessor dot next is equal to the current dot next and return true, and we'll be done. And the finalies will do our unlock for us. And otherwise, we're going to do our unlock our predecessor node. We're going to update the predecessor node with the current node. We're going to update the current node with the cur dot next, and then we're going to lock the current dot lock. So we're doing what's called hand over hand locking. So we'll hold on to one. We have two locks. We let go of one. We get another one. So it's kind of like we're climbing, right? All right. And then otherwise, you know, if we don't find the thing that we want to delete, then we leave. And likewise, with adding nodes, we must lock the predecessor and the successor, and neither can be deleted. Okay, so the invariants are easy to check, right? The tail is always reachable from the head, and it's sorted, and there are no duplicates. And that's just a repeat of the invariant. And the drawbacks are, for our fine-grained hand-over-hand locking, is that it's better than a coarse-grained lock. Threads can still traverse in parallel, but it's still not ideal because we have to do lots of acquire releases of the locks, and that can be inefficient. I guess I also feel that hand-over-hand locking is a pattern that you should avoid at all costs. Because I think, so the way that locks are safest, right, is if I have critical sections, I grab the locks that I need, I do what I have to do in a very short block of code, and then I release them, right? But if I'm holding on to them and doing one thing after another, I create opportunities for deadlock. And so I think that that anything that does something like fine-grained hand-over-hand locking, I think that's to be avoided. That's my opinion. I would not allow it. All right.
Speed of the locks, like, or the speed of the data structure when you have hand over hand.
Yes.
Versus, like, we found that as like a not very significant.
I mean, you know, the significance of the speed is going to depend on your workload, first of all, right? So the question is, how many contains do you have? How many adds and removes, and what patterns do they come in? All that stuff is going to matter a lot, right? So when you're thinking about implementations for something like this, it's almost impossible to just say, I know the best way, right? You know a way that works, you know a way that gives you reasonable performance, but if you go and check a whole bunch of different ways, you're going to find things you don't expect, chances are. But having said that, I did do some speed tests, and there are some speed tests in here. All right. Okay, so next thing we're going to try is optimistic version of the set, and that's going to traverse without locking. So we want to add add C rather. We're going to go through there, and we're going to say, aha, we found B points to D. C can clearly go in the middle. And then what we want to do is we want to lock those two things and put the C in the middle. But what could go wrong with that? Well, So right before, I first find the things, then I lock them. Oh, wait, okay. So here's me going through, right? And I find them. And now before I can lock and load, somebody else comes in and locks those two and removes B, right? And I have a reference to B and I have a reference to D, and that all looks fine to me. So I lock them, and again, things are not going to work, right? Because I'm adding C, but B is already gone, so the adding of C gets lost, right? And again, I think the way to think about this is that property of reachability um, is hanging around there, and we can't see it unless it's not physically present, and so we can't see it. And so when we go to do this check on the two locks, we don't see that B is no longer reachable. We don't see that that property has changed. All right. So what we're going to do now, we're going to do to get out of this problem is we're going to validate. So after we get B and D, we're going to go back to the beginning of the list, and we're going to check that we can still reach B. We're going to check that reachability of B, that property that isn't physically present on B, but is somehow implicitly there. All right. So what else could go wrong? So I could march over to B and D while I'm adding C, and somebody could go in there and add B prime, and that should be a B prime in there. And so now we've got, look at that stupid slide. Look at the prime is way down there for some reason. Hold on, I'm going to fix that if I can. There, got that one. Okay. All right, there's the B prime. There's the B prime. Okay, and so now I go to add C, but it's going to get me the wrong order, right? It's going to undo that B prime. So again, what I need to do when I validate, in addition to checking that B is still reachable, I have to say that the D is still reachable from B, right? And to say it's still pointing to the same place. And this is okay. And so this is my optimistic linearization point when I get the locks. And I put C in there. So we have to be careful because we may traverse deleted nodes, but we establish properties by validation after we lock target nodes. And so correctness, if nodes B and C are both locked, then node B is still accessible, and node C is still the successor to B, and neither will be deleted. And it's okay to delete and return. So an unsuccessful remove might look like this. I want to remove C. There is no C. Aha. And B is still reachable from the head. So he's checking that. I wouldn't have checked at this point. I would have just bailed for this particular thing. If I'm not actually modifying the list, I don't think I would have done that. I don't think I'd have to check. I don't believe it's strictly necessary. But for removing C, I'm going to check that B and B still points to D, and I still have it's still reachable, and so I can return false. I can't remove it because there's no C. And if both B and D are locked and B is still accessible and no D is still the successor to B, then neither will be deleted. No thread can add C after B, and it's okay to return false. So let's look at the validate method. So we're going to take a predecessor and a current node. We're going to start at the head. We're going to say while the node.key is less than or equal to the predecessor key, if the predecessor key is equal to the node, then we return predecessor.next is equal to current. And otherwise we load node with the next value, right? So that loops through until we find the the predecessor node, and then we validate it that it still points to the current. And if it doesn't, we return false. And if it does, we return true. Okay, so this is how a remove looks. So I have this retry label here on the while loop. And I'm going to get a key for the item. I'm going to say while true, node predecessor equal this.head, node cur equal pred.next, while cur.key is less than or equal to key, if item equals current.item, break. So that will break out of this inner loop. What? Oh no, this is the loop here. If current item is equal to the current item, we break, then we update the predecessor in the current, right? And so we're looking for the current item is the item that we want to remove. All right. And if the item is present, then current holds the item, and predecessor is just before current. If the item is absent, then current has to find that first higher key, and predecessor should be just before current. So it should be less than the key. And so what we do is, with the remove method, is at this point we do this try finally thing. We lock the predecessor in the current node. Then we do a validation of the predecessor in the current node. And if it's valid, and that the current item is equal to the item, then we mark the predecessor.next is equal to current.next and return true. Otherwise, we return false. And in the finally, we do the unlocks. Any questions? Are you with me?
Happens if it doesn't, because we just don't.
If it doesn't validate, right, then what we're going to do is we're going to retry. We're going to go back to that retry and start again. So we want to do is we want to have validate work, right? We want to get to the predecessor and current that we know we're supposed to have, and validate succeeds, and then we can be done with it. Otherwise, we just keep trying.
Keep trying. Like if it doesn't validate, we'll try and search the list again to see if we can.
Right. If it doesn't validate, that means it's something concurrent changed something while it was looking, and it just tries again.
How many times we try just once?
No, it's got a while loop. It can just keep doing it. It's kind of like so which progress condition do you think you would call this? So I guess I would call it deadlock free. The point is it can just keep getting knocked back, right, by somebody else modifying the thread. And we have to choose between starvation free and deadlock free because we're using locks. And if we're using locks, that means we've got a blocking protocol anyway. So wait free and lock free are out the window. All right. So optimistic lock has limited hotspots, targets of add, remove, and contains. There's no contention on traversals. And the traversals are wait free, which is nice, but we might have to do lots of them. Much less lock acquisition and release, which should be a boon for our performance and concurrency. And the problem is that we definitely need to traverse the list twice, and the contains method is acquiring locks. So the optimistic is effective if the cost of scanning twice without locks is less than the cost of scanning once with locks. And the drawback is that contains acquires locks and 90% of the call, and that's 90% of the calls in some apps, right? And they say in many apps. So any questions on optimistic locks? All right. So next is the lazy. So lazy is like optimistic, except it's scan once and contains X, never locks. And the key insight is removing nodes causes trouble, so we're going to do it lazily. Remove is going to scan the list as before. It's going to lock the predecessor and the current as before, but it's going to have a logical delete. This is the new part. It's going to mark the node as removed. And then there's a physical delete where we redirect the predecessor's next bit. And this is actually the key thing, the key insight into this whole problem is that this state that we've been dealing with implicitly, we're now making it explicit. We're now making it something that we can see and keep track of. And that makes all the difference in the world for making this algorithm simpler. So the lazy removal looks like this. If the thing is present in the list, then that bit is green. And if it's deleted, the bit is red. And so I can do a physical delete if I know that. So after I do the logical delete, I can do the physical delete. And so we scan through the locked and the marked nodes, removing a node that doesn't slow, removing a node doesn't slow down the other method calls. But we still have to lock the predecessor and current nodes. But there's no need to rescan this list. We check that the predecessor is not marked, the current is not marked, that the predecessor points to the current, and then everything is good. So business as usual, right? We're going to go through here, and we want to remove B. I'm sorry. We want to remove B, and A is not marked and B is not marked. Then we can do the logical delete, and then the physical delete, right? But now B knows that it's deleted because that implicit state that was never really physically manifested is now present. And so when this green one wants to do an add or a remove or something, it's going to see that B is deleted. And all the kinds of problems that we've been dealing with go away. So the validation method, think how complicated the optimistic validation method was. This is the validation method for the lazy lock. We check that the predecessor is not marked, that the current is not marked, and that the predecessor.next is equal to the current. The end. So I think I lied. We might have to repeat in this case. We're still going to validate as before, and we're going to check that the current key is equal to the key, and then we're going to say that if this is for the remove, we're going to set the marked bit to true. Then we're going to set the predecessor next to the current.next, and then we're going to return true. And so we're doing this one additional step, but it makes all the difference. So now the contains method, we can say, while cur equals this head, cur.key is less than key, cur equal cur.next. And at the end, we say, if cur.key equals the key and the current is not marked, then we've found it. The contains worked. So it's much simpler. So the summary is the wait-free contains uses a mark bit in the list ordering, and not marked means not in the set, and marked or missing means not. And whether it's marked or missing, then it's not in the set. So the key thing in this one is this marked bit, but I think it's the insight is that the marked bit was kind of there all along. We just couldn't see it until we made it physical. All our algorithms and complexity up until this point has been based on the invisible presence of that marked bit, if you want to think about it that way. All right. Any questions? All right. Finally, we have the lazy list. And the lazy has add and remove plus a wait-free contains. And the good is the contains doesn't lock. In fact, it's wait-free. It's typically the highest percentage of methods are contains methods. Uncontended calls don't retraverse, and the bad is contended add and remove calls do retraverse, and there can be a traffic jam if one thread delays. So any concurrent data structure based on mutual exclusion has a weakness. If one thread enters the critical section and the other, I love this phrase, eats the big muffin, that's a cache miss or a page fault or it's descheduled or something like that, then everyone else that using that lock is stuck. And so you need to trust the scheduler. But with lock-free data structures, no matter what, you can make progress in any execution. Some thread will always complete a method call, even if the others halt at malicious times. Implies that the implementation cannot use locks. No locks. So the next step is lock-free lists. So we're going to have a wait-free contains, a lock-free add and remove, and we're going to use only compare and set. What could go wrong? So we're going to use cast to verify that a pointer is correct. We have a logical removal. We have a physical removal. Not enough, because we can do a logical removal at this, and something else can do a cast at the wrong moment, right? Remember, we don't have locks here, so in between steps of checking one thing and changing another thing, something else can happen. And so the solution is to combine the bit and the pointer together. And there's this class in Java called the atomic markable reference. Okay, so it's the logical removal plus set mark bit. And so the cast is going to fail if you've got the mark bit wrong. And so let's see how this looks. So we're going to atomically swing the reference and update the flags. We're going to remove in 2 steps. We're going to set the mark bit and then redirect the predecessor's next pointer. So the atomic markable reference class looks like this. We've got an address and then 1 bit in the address that isn't used for anything, and we're going to use that. That's going to be our mark bit. And we're going to, the method, because Java does not allow you to have multiple return values, the method is going to return the object reference, but it needs to be passed a Boolean array so that it can return the marked bit. So you have to allocate a Boolean array and pass it there to get that back. I wish I had tissues. You can also call an isMarked thing that will just get the status of the marked bit. And so changing state, we can say compare and set is going to take 4 arguments. We're going to have expected reference and updated reference, expected mark, and the update mark. Okay, so we can do those things atomically at the same time. And so if we have the current expected reference and the current expected mark, then we'll get the new object reference and the new mark. And then we have an attempt mark where we can say, if this is the current reference, then change to this new mark. All right, so to remove a node, we want to remove C. We're going to change that bit, and then we're going to switch that pointer, right? But we have no locks. And somebody else might want to remove B. So we have to make sure that these things both work. So they're both going to come in there, and they're going to mark the object is removed. And then they're both going to attempt to do casts, but the remove C is going to fail, right? Because B is now deleted. And its expected value was not deleted. All right. So, so the remove B failed, and then the remove C can retry and then succeed. So what do you do when you find a logically deleted node in your path? A, answer, you finish the job, cast the predecessor's next field, and proceed by repeating as necessary. So the lock-free traversal, only for add and remove, is like this, right? We start here, we go through predecessor current, and then we see something, we see a predecessor and a current, but our current is deleted. So what we're going to do is we're going to do a cast to remove it and swing around it, right? And then we're going to march from there. So we're going to have this thing called the window class. And it's got a predecessor and a current, and it takes a predecessor and a current to instantiate it. And so basically it's just a container for those 2 values. And then it's going to have a find method. And you're going to hand it a head and a key. and it's going to give you back the predecessor and the current. So, oh, geez, look at this. All right. Um, okay, so what we're going to do is we're going to find the window where we have the predecessor and the current is pointing to the item at some instant. And then we're going to we're going to find this predecessor and current successor, right? And then we're going to set the current. Well, so here's. I'm not sure what this slide is trying to tell me now that I look at it. Let's just look at the code. So here's the remove. We're going to create a while true loop. We're going to do a find of the predecessor and the current. If the current key is not the key we're looking for, we're going to return false. Otherwise, we're going to say the current get next reference, the current.next.get reference, because we have an atomic reference there, atomic markable reference there. And then we're going to say, current next compare and set successor false true, right? So what we're going to do is we're going to check that the successor is still the successor, but we're going to change the bit to true to mark the node as deleted. So this is how we mark it, right? And then if that fails, we're going to have to retry because that means somebody else is messing with us. And now if it succeeded, then we're going to take the predecessor.next current is going to swing to become the successor. And we're going to change to make the bit false. All right. Are we good? Okay. And now we have an add method. We're going to check to see that the current key is the key we're looking for. And if it's already there, we're going to return false. Otherwise, we're going to create a node for the item that we're going to insert. We're going to say node dot the next node on the node we allocated is going to be an atomic markable reference with current to false. And then we're going to do a compare and set from the predecessor's next field from the current node to the node that we allocated. And if it succeeds, then we've successfully added the node. Otherwise, we have to try again. We have to go into the retry loop. And then we have our wait free contains where we just look for the key and we just do the cur.next.get marked. And if the current key is the key and the marked bit is not set, we win. And then we have to look at the window method, the find method on the window method, which is a little more complicated than we might hope. So we have our retry loop with a while, and we have the predecessor is equal to the head, and the current is going to be the pred.next.get reference. And then while true, we're going to say current successor equals current.next.get marked, right? And then if it's marked, we're going to have some logic that goes in this while loop. And then if the current key is greater than or equal to the key, then we're going to return the new window. And if not, we're going to update the predecessor and current and keep going through the loop. So, all right. So if the thing is marked, right, if we find the thing is marked, then we're going to try to set the next pointer on the predecessor from the current to the successor. And we're going to try to say false, false, right? So we want to maintain that the predecessor is not deleted while we do this. And if we fail, then we have to retry. Otherwise, we can update the current with the successor and the successor with current.next.get marked, and then we can potentially continue in this while loop. So as long as there are things ahead of us that are deleted, we can keep chopping them out. Okay, and the performance on a 16 node shared memory machine, they did a benchmark with this stuff, and they had a high contains ratio, 90% reads, and this was the performance curves they got. The lock-free list was the best, the lazy list was next, and then fine and coarse. And then a lower contains ratio, which is 50%, they got something similar, but they're closer together. And as the contains ratio increases, generally speaking, the lock-free and the lazy show increased performance. And so there's a summary. We have coarse grain, fine grain, optimistic, lazy, and lock-free synchronization. And next time we can go over some of the code for this and look at the second part of the homework and maybe have a quiz. Who knows? Any questions? All right. That is a wrap.